Hey guys, Ms. Gosling here. In this video, you are going to learn about resolution. By the end of the video, you will be able to define and solve all of our world peace problems by being able to use your new conflict resolution skills. I kid, of course. By the end of the video, you will actually be able to define and solve problems involving resolution in the physics sense rather than the conflict resolution sense. So let's go ahead and start by defining resolution. And we're going to define resolution as the ability of an imaging system. So, for example, the pupil of your eye, the lens of a telescope, and other similar systems through which we see objects. Resolution is going to be the ability of that imaging system to produce two separate, distinguishable images of two separate objects. So, the reason that we need to even talk about resolution at all is because when light passes through an aperture of some kind, so a lens, a slit, the hole in your eye of your pupil, we know that light diffracts. And as a result, rather than having a nice, clean image of our object, what we have is a picture of the object, an image of the object, surrounded by a halo of light from that diffraction pattern. So when we have two images, it can be very easy for our two images to not be distinguishable as they are in the right. So for example, if I am looking at two letters on a street sign, I may or may not be able to tell whether they are different letters or not, depending on whether they are resolved. So as somebody who wears eyeglasses, I can tell that my glasses help me resolve street signs. They help me resolve the image of multiple letters on a sign. Other folks who wear glasses, you probably wear your glasses for similar reasons. So when we talk about resolution, what we want to be able to see is our two separate objects clearly and distinctly, as in the middle picture here. So again, the picture on the right here is an object that is not resolved. The picture in the middle is our two objects who are just barely resolved, because I can just barely tell that I have two separate objects. And we're actually going to have a very specific definition of that moment when our images are just barely resolved. And we're going to call that Riley's criterion. And again, that is the moment that our two objects will become fully resolved. Or more accurately, the moment the image of our two objects, is fully resolved. So we're going to define that as the moment when the principal maximum from one diffraction is no closer than the first minimum of the other pattern. That is, we can see where the minimum of our second pattern is, and we want our first maximum to be no closer to our second image than that. So here is the minimum of our second image, and you can see that is exactly where the maximum of our first image is. And so that is where we know that our images are just barely resolved and have reached Riley's criterion. On the right, we can see what the two images will look like if they're unresolved. And you can see they are very overlapped, so they look like maybe one image. Whereas on the left, we have a graph of a fully resolved, clear picture, where the maxima are clearly separate. So for a single slit with a circular aperture, so for example, the human eye, we are going to define theta, or the minimum angle of resolution, which is going to be given in radians, as 1.22 times the wavelength of light divided by the diameter of our aperture. So, for example, the diameter of the pupil of the eye, or the diameter of the lens of a telescope. And you'll note I mentioned telescopes. Resolution is a really important part of defining a really important factor to take into account when we're designing telescopes, because we want to ensure that every star that we see is fully resolved. So let's go ahead and go through an example. Jack observes two distant point sources of light. The wavelength of each source is 555 nanometers. The angular separation between these two sources is 2.5 times 10 to the negative fourth radians at the pupil's eye. Estimate the diameter of the circular aperture of the eye if the two images are just resolved. So let's go ahead and start, as always, by listing out our givens. So we know that the wavelength of each source, lambda, is 550 nanometers, or 550 times 10 to the negative 9th meters. We also know that the angular separation between our sources, theta, is 2.5 times 10 to the negative fourth radians. Note, if this was given in degrees, it is important that this is given in radians. If it was given in degrees, I would need to convert from degrees to radians. So those are my givens. Let's go ahead and list out my unknown now. So this question is asking me to estimate the diameter of the circular aperture. So that means that A, the diameter, is my unknown. Using this, I can figure out that the equation I'm going to use to solve this problem is Riley's criterion, or theta is equal to 1.22 times lambda over A. Thus, using this to solve for A, I can multiply both sides by A, divide both sides by theta. My thetas on the left side will cancel, my A's on the right side will cancel, giving me A is equal to 1.22 lambda over theta. And now that I have my equation nicely solved for my unknown, I'm ready to finish subbing and solving with my numbers. So I know that A is equal to 1.22 lambda, or 1.22 times 550 times 10 to the negative 9th over theta, 2.5 times 10 to the negative 4th. So from that, I am ready to throw this into my calculator and solve for A. And when I do that, I get that A is equal to 0.002 meters, or 2 millimeters. And there you go, guys. We have now used Riley's criterion to figure out the diameter of the pupil. So one other equation that I do want to introduce you to is Riley's criterion for a diffraction grating. So a diffraction grating is something with a series of different slits in it. So rather than a single hole, we have many different holes that our light can travel through. So for a diffraction grating, we are going to define resolvance, or how well the diffraction grating can differentiate between different wavelengths of light. So, for example, can this diffraction grating differentiate between red light and yellow light, or can it only differentiate between red light and blue light? So we're going to define resolvance as the ratio of the wavelength of the light to the smallest difference in wavelength that can be resolved by the grating. And that is equal to the number of slits times the order of the diffraction. So again, N is number of slits. And we're going to define M as the order of the diffraction. So are we looking at the second order, the third order, the first order, and so on and so forth? Note, the larger that R is, the better the device is at resolving. So again, bigger R equals better resolution. So I know this seems a little weird. We're introducing a bunch of new variables that you haven't had to look at, but let's go ahead and take a look at an example problem, and I think this equation will make a lot more sense. Okay, so example 2. Two lines in the emission spectrum of sodium have wavelengths of 589 nanometers and 589.6 nanometers. Calculate the number of lines per millimeter needed if the lines are to be resolved in the second order spectrum with a beam width of 0.10 millimeters. So let's go ahead and start, as we always do, by listing our givens. So I know that the first wavelength of light is 589.0 nanometers, and the second is 589.6 nanometers. I also know that m, my order, is 2, and that the width of the beam is 0.10 millimeters. So moving forward to my unknown, I am trying to find the number of lines per millimeter. So here's what I'm going to have to do. And I'm going to list this in my equation stage, even though some of this is not going to be equations. So first of all, I need to find how many slits need to be in the beam. So how many slits does the beam need to go through? And I can use that. I can find that using my equation for resolvents. R is equal to lambda over delta lambda, which is equal to n times m. Then, using that, I need to figure out, okay, so I know how many slits are in my 0.1 millimeter beam. How many slits are going to be in 1 millimeter? And for that, what I'm going to have to do is I'm going to say, okay, so there's x slits. So there's n slits, which I will calculate in step 1, per 0.1 millimeter. And that has to equal the number of slits in per millimeter divided by 1. So that's how I'm going to be solving this problem. So let's start my sub and solve with my first equation. Lambda over delta lambda is equal to n times m, or n is equal to lambda over m times delta lambda. Plugging in my numbers, I am going to go ahead and start by plugging in lambda, and for that I can pick either lambda 1, lambda 2, or the average of the two. I'm going to go ahead and just go with lambda 1 because it's a nice round number, which I prefer. So that's going to be 589.0 times 10 to the negative 9th. And I'm going to divide that by m, or 2, times the difference in my wavelengths, which is going to be 589.6 minus 589.0, or 0.6 nanometers, or 0.6 times 10 to the negative 9th meters. And plugging it in the calculator, I'm going to get n is equal to 491 lines. Now, I'm ready for step 2. So I know that n, or 491, divided by the space in which I need to have those 491 lines, so 0.1 millimeters, is equal to x, or I'm going to say n, the number of lines that I need per millimeter, divided by 1. Thus giving me that n is equal to 491 over 0.1. Plugging that into my calculator, I get that I get that n is equal to 4,908 lines per millimeter. Now, I'm gonna note here, you're probably not gonna be able to find a diffraction grading with 4,908 lines per millimeter. So if you need to choose a diffraction grading, you're always gonna go to the next highest number of lines per millimeter. So in this case, likely 5,000 lines per millimeter. And there you go, guys. That is how we can figure out problems involving resolution with diffraction gratings. So let's go ahead and talk takeaways. First of all, resolution occurs when you can discern the image of two separate objects. And Riley's criterion tells us the minimum aperture size needed to resolve an image. And again, we're going to use this for single slits, so for a single aperture, as in the lens of your eye, the lens of a telescope, something along those lines. When we have a diffraction grating, of course, we start talking about resolvents instead. So with that, I'm going to go ahead and let you guys go. Try solving some problems. Best of luck and happy solving.